Okay, so I'll be talking about approximating k-edge connectivity problems with the new iterative relaxation technique called ghost value augmentation. I'm Nathan, and this is joint work with Alice Hershkowitz and Rico Zenklusen. The primary problem we study is the k-edge connected spanning subgraph problem, or KECSS. And as input, we get a weighted graph G, like this one, and a parameter k, and the goal is to select the cheapest subset of edges which k-edge connects the graph. So even if you're not familiar with this problem, I promise you do know it for k equals 1. Okay, so for k equals 1, this is exactly the minimum spanning tree problem. And here's a solution for that problem. So clearly this problem is easy, computationally easy for k equals 1. But it turns out that for k at least 2, this is already APX hard. In other words, for k at least 2, this problem is NP hard. And for all k, there's no approximation algorithm with ratio better than something like 1.01. So here's an example solution for k equals 2. The best known approximation algorithm for this problem gives a factor of 2. And this has been known since the 80s and is obtainable through several methods, for example, using Jane's iterative rounding technique. And a major open question is whether there's a better than 2 approximation for any k at least 2, even for, say, k is 100. And we became interested in this question for large k, and in particular we asked, what if instead of losing on cost, we could instead lose a little bit on connectivity? So in particular, we wanted to know, can we find a k minus order 1 connected solution with cost no more than that of the optimal k-edge connected solution? And for large k, this is actually quite appealing, right? So if I want to design a highly connected network, say 1,000 edge connected, I would probably prefer to lose nothing in cost and get a 990 edge connected graph, rather than pay twice as much just to get that last 10 units or order 1 units of connectivity. And this is what we show with a constant of 10. So in particular, we show that there's a polynomial time algorithm that produces a k minus 10 edge connected solution with cost no more than that of the optimal k edge connected solution. And our approach is to round a solution to this k-edge connectivity linear program, but just asks that every cut in the graph has at least k edges going across it. So here's an example solution for k equals 2. And our main technical theorem is that given a solution to this LP, we can round it in polynomial time to an integral k minus 10 edge connected graph of no greater cost. And this immediately implies the main theorem, since we can run this linear program, obtaining a lower bound on the cost of opt, and then round the solution we get to obtain a k minus 10 edge connected graph using this theorem. A closely related problem known as KECSM is the same as KECSS, except we're allowed to take every edge as many times as we'd like at the same price. So for example, this is a KECSM solution, a 2ECSM solution, but not a 2ECSS solution since we double one of the edges. And for a long time, the best known approximation algorithm for this problem had a ratio of 3/2, until recently with Carlin, Ovescaron, and Zhang, we showed a 1 plus order 1 over square root k approximation. In other words, we show that this problem gets much easier as k grows. And recall that no such result is possible for KECSS, since it's APX hard for all k, right? So even for k is 1,000,000, we cannot get a 1.01 approximation for KECSS. On the other hand, we show that for KECSM, we can get arbitrarily close to 1 as k grows. And this approximation algorithm with ratio 1 plus order 1 over square root k was motivated by a conjecture of Pritchard that there's a 1 plus order 1 over k approximation. And it turns out that our main technical theorem immediately proves this conjecture. So why is this the case? Well, first we can solve the k connectivity LP, which is the same for KECSM and KECSS, except we just drop the upper bound on the edges for KECSM. And then given a solution to this LP, we then scale every edge by a factor of 1 plus 10 over k. And now the graph is k plus 10 edge connected. And this is feasible for the KECSM LP because there are no upper bounds on the edges. But now I have a fractionally k plus 10 edge connected graph. And so I can just apply our technical theorem to obtain a k edge connected graph of no greater cost. And we only lost a little bit in the cost because we paid this 1 plus 10 over k factor in scaling. Pritchard also asked if this conjecture was tight. So in other words, if there was a matching hardness result. And we also proved this. So we demonstrate that there's no approximation algorithm for k ECSM with ratio asymptotically better than 1 plus order 1 over k. So let's kind of summarize where we're at. So we proved that we can produce a k minus 10 ECSS of cost no more than that of the optimal k ECSS, which you can think of as kind of a resource augmentation result. And this complements the existing 2 approximation. We also know that there is no approximation algorithm with ratio going to 1 as k grows for k ECSS. This was proved by Pritchard. For k ECSM, we get 2 results. We first use our rounding theorem to show that we can obtain a 1 plus 10 over k approximation, improving upon the previous 1 plus order 1 over square root k. And we also prove a matching hardness lower bound. I also want to mention the unweighted case, which actually behaves quite differently for k ECSS. So in fact, for k ECSS, here there is an approximation algorithm with ratio going to 1 as k grows, but we know this is impossible for the weighted case. So these problems have a clear separation. On the other hand, we now know that weighted and unweighted k ECSM, they're actually quite similar. Okay, so in the remainder, I'm going to talk a bit about the proof of this rounding theorem. And before we get started, I want to mention kind of what existing results would give you for this problem. In particular, the Nash-Williams theorem will give you a bound of k over 2, since it shows that any fractionally k-edge connected graph is in k over 2 times the spanning tree polytope. And actually, this theorem is tight, so we cannot get k over 2 plus 1 spanning trees. So this shows that something is possible. We can get k over 2, but to get close to k, we're going to need a different approach. The approach that will work is iterative relaxation, which I'm going to introduce now. And it's one of my favorite techniques, so I'm going to spend a few minutes on it. So iterative rounding was first introduced by Jane in 2001. And to the best of my knowledge, the first paper on iterative relaxation was from Singh and Lau from 2007. And iterative relaxation is basically iterative rounding without any rounding. So what's the idea of this technique? Let's consider a generic LP with n variables and 2n trivial box constraints that just ask that the variables lie between 0 and 1. So in other words, these box constraints I've drawn below. And then let's say there are m non-trivial constraints. So in this case, there are 4. A well-known fact is that in any extreme point solution to this LP, there are going to be exactly n linearly independent constraints met with equality that uniquely define x. Right? So if I'm optimizing, say, in this direction, maybe I find this extreme point, and it's defined by these 2 non-trivial constraints in this case. And here's a simple observation. If n is greater than m, then there's always a trivial active constraint. In other words, there's always some xi that's set to 0 or set to 1, right? So if I have n equals 2 variables, and only 1 constraint, and I try to optimize, I'm always going to hit a point which is on the face of one of the faces of this box. So this suggests the following framework. First, if there's a variable set to 0 or 1, let's fix it to that value, delete it, and update the constraints. So for example, here we hit a face of this box. Now I'm going to fix x1 to 0 for the remainder of the algorithm and continue rounding on this lower dimensional space. Or to give a slightly more interesting example, here we have a 3-dimensional space. Here we hit one of its faces, and now we'll continue rounding on this 2-dimensional space. Okay, so that's kind of the easy part. The interesting case is what happens when we do not hit a face of the box. Instead, we hit n linearly independent, tight, non-trivial constraints. In this case, we're going to find a constraint that's somehow safe to delete. So this is part of the framework that's problem specific. And once we find this constraint, we'll delete it. So I'm going to remove this green one. And then we'll continue optimizing. And then again, we'll hit step 1. And then maybe we'll drop more constraints and keep going. And in this way, we're eventually going to produce an integer point of cost no greater than the initial one. So the core of any iterative relaxation argument is to show that when we're in this case with no box constraints defining our point, then one of these n linearly independent constraints is somehow safe to drop, safe to ignore. So either it's approximately satisfied by the variables already set to 0 or 1, or maybe it's approximately implied by the constraints that remain. And this allows us to make progress, right? The reason we need this is that it allows us to delete a constraint and move forward. Otherwise, we would just be stuck right at this fractional point. All right, so I'm going to tell you about how this framework usually looks for graph problems and kind of why it doesn't immediately work for our problem here. So first, we argue that the tight constraints at a particular extreme point can be uncrossed to form a laminar family L. And a family is laminar if for every 2 sets, either they're disjoint or one is a subset of the other. So like in this picture. Okay, so what does this mean? When we have no tight box constraints, we have a bunch of tight constraints defining the point. There can be many more than n, but of course at most n linearly independent ones. And the first step is to show that there's a laminar family of these tight constraints such that their corresponding, a laminar family of tight sets such that their corresponding constraints are all linearly independent and span all of these tight sets. The second step is then to use this laminar structure to show that some constraint in this family is very close to being satisfied. In particular, here we would want to show that there's a set with at least k minus order 1 edges set to 1. So its connectivity is already fixed to be at least, let's say, k minus 10. And now it's safe to drop that set and iterate. It turns out we actually don't know if this simple recipe works or not. And proving or disproving this is a very interesting open question. So why don't we know if this works? Well, there's some good news about this approach. We can actually always perform step 1 so long as the minimum cut of the graph is k. And this is because the set of minimum cuts of any graph are very well structured. So at the beginning of the algorithm, we have a fractionally k-edge connected graph, and our constraints are going to be minimum cuts of this graph. So at the beginning of the algorithm, I can always perform step 1. And in fact, as long as we can perform step 1, it's very easy to prove that step 2 holds as well. So this sounds great. Why aren't we done? Well, the bad news is that after dropping some constraints, the minimum cut of this graph may drop below k. And at this point, step 1 fails, and we don't know what to do. So let me explain these two things in a little more detail. So uncrossing works on the set of min cuts because the cut function is symmetric submodular or posi-modular. And actually, you can use submodularity as well, but in this talk, I'm going to use posi-modularity. Okay, so given 2 tight constraints, s and t, we know that 2k is equal to delta of s plus delta of t, where I'm kind of ignoring the fact that I have this vector x giving the weight of the cuts. And now applying posi-modularity, this is at least delta of s minus t plus delta of t minus s. And now, since the graph is k-edge connected, each of these quantities is at least k. But now, if I add s minus t and t minus s to our family of linearly independent constraints, it's actually safe to remove t. And this is because I can now write t as s minus t plus t minus s, right? Because this is actually all equalities. And so now I've reduced the number of crossings, and I can keep iterating this until I get a laminar family. Unfortunately, if we try to do this for a graph which is not k-edge connected, so the minimum cut is below k, things break down. I can try to do the same thing, but now I can no longer bound these 2 quantities by k, and so I cannot say that delta of t is spanned by these 3 sets. And in fact, there are even bigger issues here because S minus T and T minus S are not necessarily tight. I may have dropped these previously in the algorithm. And in that case, we couldn't really put them in our family. But even if we could, we would have this issue that T is not spanned by these three sets. And to give you a real example here, let's look at these sets S and T. So suppose the blue edges are integral and the dotted edges are fractional. Therefore, here we may have dropped S minus T and S intersect T, since they both have many integral edges. Let's say our threshold for dropping a set is at least K minus 10 integral edges. But S and T have both not yet been dropped. And now you can see that T is not equal to S minus T plus T minus S, right? In particular, this special edge A coming out of the center is only going to appear negatively on the right-hand side. Okay, so now I'll tell you how we fix this issue. We will show that either there exists a minimal tight constraint S with many integral edges, and actually few fractional edges. That turns out to be important. Which also is safe to drop because the edges inside any minimal tight constraint are all integral. So kind of by dropping this set and contracting it, I actually haven't messed up any of the sets inside. Okay. Or if such a set does not exist, we show there must be two vertices in this possibly contracted graph, right? In step one, we may have contracted some of these sets. There may be two vertices in this contracted graph, which share many edges between k over 2 minus order of 1 and k over 2, but strictly less than k over 2. And in this case, we perform what we call a ghost value augmentation. So we just tell the linear program that there are actually more edges between these two vertices. We boost up the value to k over 2. And notice we cannot put these edges in our solution because they may not even exist in the graph. And our key observation is as follows. So long as the only cuts that are less than k in the graph are the vertices, which is true for us since we always contract sets that we drop, then the only barrier to uncrossing, this step one we mentioned before, is these vertices that share almost k over 2 edges, but not quite. So let's return now to our previous bad example. And look at these pieces, S minus T and S intersect T. The connectivity of both of them is below k. So it must be that we previously dropped these sets and then contracted them into singletons. And indeed, in this example, as we're able to prove, they share many edges, in this case, k over 2 minus 4. So we can perform our ghost value augmentation. And finally, we prove that after removing the ghost edges, the connectivity of the graph does not go down too much. And roughly speaking, this is because the ghost edges only ever increase the connectivity of a bundle of edges by a multiplicative order 1 over k factor, right? So I've only taken a large group of edges, a value close to k over 2, and added a small number of edges. But to recap the algorithm, Ellis made a nice drawing of the situation. So given an extreme point solution, we showed that either we can always either contract a minimal tight set, which has all integer edges inside, like this blue set on the left, with the additional property that the boundary of this blue set has few fractional edges. Otherwise, we show such a set does not exist, then there must exist a pair of vertices that share many edges, and then we can perform a ghost value augmentation. And again, here's our main rounding theorem. There are a few interesting questions that arise. So first, does this theorem have more applications? In a nutshell, what we showed is that for large K, fractional connectivity is essentially the same as integral connectivity, which I think could be a very useful fact. Second, it would be great to see more applications of ghost value augmentation in network design, in particular in places where uncrossing is challenging. And finally, a very interesting open problem is whether this constant 10 can be improved to a 1. We don't know any barriers preventing this. So thanks for listening.